Hey everyone. Tonight we begin with something a little different. Something that's going to make you step outside later and look up at the sky with entirely new eyes. We're diving into one of the most terrifying hypothetical scenarios in all of astronomy. What would happen if our moon, that familiar glowing companion that has watched over humanity since the first person ever tilted their head toward the heavens, simply vanished? Forget everything you think you know about the night sky. The truth is, the moon isn't just a pretty ornament hanging in the darkness. It's the silent guardian that makes life on Earth possible, and without it, well, you probably wouldn't survive long enough to miss it. So before we get started, take a moment to drop a comment below and let me know where you're rewatching from tonight and what time it is where you are. Let's start with the basics, shall we? That thing you see hanging in the night sky, roughly 384,400 kilometers away on average, isn't just a rock. It's not just a satellite. It's not just the thing poets write about or werewolves howl at in horror movies. The moon is, without exaggeration, one of the primary reasons you exist. Think about that for a moment. Every breath you take, every sunrise you've witnessed, every stable season that allowed crops to grow and civilizations to flourish, all of it is connected to that silent sphere of ancient rock and dust. The moon doesn't just reflect the sun's light to illuminate your midnight walks. It actively participates in making Earth a place where complex life can thrive. Our moon is massive, relatively speaking. It's about 1/4 the diameter of Earth, which makes it the 5th largest moon in our entire solar system, and the largest relative to its host planet. Jupiter's moons may be bigger in absolute terms, but compared to the giant they orbit, they're specks. Our moon is more like a dance partner than a subordinate. In fact, some astronomers argue that the Earth-Moon system should technically be classified as a double planet. The moon formed roughly 4.5 billion years ago, likely from the debris of a cataclysmic collision between the young Earth and a Mars-sized body. Scientists have named Theia. Imagine that our planet was struck by something almost as large as Mars, and the violence of that impact threw so much molten rock into space that it eventually coalesced into the moon. From destruction came creation. From chaos came stability. From cosmic violence came the conditions for life. But here's what most people don't fully appreciate. The moon isn't passive. It's constantly working, pulling at our oceans, stabilizing our axis, slowing our rotation, and shielding us from the worst of space's indifference. Without it, Earth would be a fundamentally different world. A world where you and I would never have evolved. A world of chaos. So what happens when you remove this cosmic guardian from the equation? What unfolds when that familiar glow disappears from the night sky forever? The answer is nothing short of apocalyptic, and it happens faster than you might think. Imagine you're standing outside on a clear night, gazing up at a full moon. The silvery light bathes everything in that ethereal glow humans have romanticized for millennia. And then, in an instant, it's gone. No dramatic explosion, no warning, just there 1 second, absent the next. Poof. Vanished. The darkness that floods in would be immediate and profound. your first reaction would probably be confusion. Maybe you'd blink, rub your eyes, assume a cloud passed over. But the sky would be clear. Stars would suddenly seem brighter, yes, but there would be this gaping void where the moon used to be. That familiar landmark of the night gone. Your brain, so accustomed to expecting it, would struggle to process the absence. But within that first second, the gravitational relationship between Earth and its missing companion would already be unraveling. You see, the moon's gravitational pull creates what scientists call tidal forces. Essentially, a gentle but constant stretching of Earth's shape. The planet isn't perfectly round. It bulges slightly toward the moon. The oceans bulge even more dramatically, creating the tides we observe every day. The moment the moon vanishes, that gravitational tug disappears. And here's where physics gets terrifying. The oceans, which have been pulled into their current shape by the moon's gravity, would suddenly be released from that pull. It's not like they'd immediately settle into a calm, uniform layer around the planet. No, the momentum of the water, the existing currents, the rotational forces of Earth itself, all of these factors would create chaos. Think of it like this. Imagine you're spinning a bucket of water in a circle, and suddenly the bucket vanishes. The water doesn't just gently fall, it goes everywhere, violently. The oceans would begin sloshing, rebalancing, seeking a new equilibrium. But that process wouldn't be peaceful. It would be catastrophic. Let's talk about tides. Because most people dramatically underestimate how much the moon influences our oceans. Twice a day, the moon pulls billions of tons of water toward it, creating high tides. When the moon is on the opposite side of Earth, centrifugal forces create another high tide there too. The result is a rhythmic, predictable rise and fall of sea levels that has governed coastal life for as long as there have been coastlines. The sun also contributes to tides, but its effect is only about 46% as strong as the moon's, despite the sun being vastly more massive. Why? Distance. The moon is so much closer that its gravitational gradient across Earth's diameter is significantly stronger. When the sun and moon align during new and full moons, we get spring tides, the highest highs and lowest lows. When they're at right angles, we get neap tides, more moderate fluctuations. Now, remove the moon entirely. You haven't eliminated tides, but you've reduced them to roughly 1/3 of their current strength, driven only by the sun. But here's the problem. The transition wouldn't be gradual. The existing tidal bulges, the massive walls of water currently held in place by lunar gravity, would need to redistribute. In the hours following the moon's disappearance, coastal regions around the world would experience unprecedented flooding and strange, erratic water movements. Some areas that were previously experiencing high tide would see sudden drops in sea level as the water rushed elsewhere. Other regions, particularly near the equator, would see walls of water arrive, seemingly out of nowhere. Scientists have modeled what this might look like, and the results are grim. Initial waves wouldn't be tsunamis in the traditional sense. Those are caused by displacement events like earthquakes. These would be something different. Massive, continent-wide shifts in water distribution. Coastal cities would flood, harbors would drain, ships would be stranded or capsized. The chaos would last for days as the oceans slowly, violently found their new equilibrium. But the immediate flooding is just the beginning. The long-term effects on tidal ecosystems would be devastating. Tidal zones, those rich biological boundaries between land and sea, are home to countless species that have evolved over millions of years to depend on regular tidal rhythms. Crabs, mollusks, certain fish, seabirds that feed in tidal flats, all would find their habitats fundamentally altered. Many wouldn't survive. Mangrove forests, which require tidal flushing to survive, and which protect coastlines from erosion and storms, would begin dying off. Coral reefs, already stressed by climate change, would face additional trauma from altered water circulation patterns. The marine food chain, which supports billions of humans who depend on seafood, would begin collapsing link by link. Once the initial chaos of the tidal disruption begins settling, a different kind of crisis would emerge. One that might seem trivial at first, but would prove profoundly disorienting. The darkness. You've never truly experienced dark until you've experienced moonless dark. Even on nights when the moon is new or hidden by clouds, its light still reflects off atmospheric particles and the landscape itself. A moonless night in a remote area away from artificial light is dark, yes, but it's nothing compared to a world permanently without lunar illumination. The moon, at its brightest during a full phase, provides about 0.25 lux of illumination, roughly equivalent to a candle burning 9 meters away. That doesn't sound like much, but it's enough for human eyes, which are remarkably adaptable to navigate terrain, recognize faces at close range, and perceive the general shape of the landscape. It's enough to hunt by, enough to travel by, enough to have shaped human behavior for hundreds of thousands of years. For much of human history, the moon was our primary source of nighttime light. Ancient cultures planned their activities around lunar phases. Harvest moons allowed farmers to work into the night during crucial crop seasons. Military campaigns were launched under full moons to enable nighttime maneuvers. Even our languages bear witness to this. The word month derives directly from moon, reflecting how central lunar cycles were to our timekeeping. Without the moon, nights would be dominated only by starlight, providing perhaps 0.002 lux of illumination on the clearest nights, over 100 times dimmer than moonlight. For people in developed areas with abundant artificial lighting, this might seem manageable. But remember, roughly 1 billion people worldwide still lack reliable access to electricity. For them, moonlight isn't romantic. It's essential. And it's not just humans who depend on moonlight. Countless species have evolved behaviors tied directly to lunar illumination. Sea turtles use moonlight reflected on the ocean to find their way from nest to sea. Many coral species spawn based on lunar cycles, releasing eggs and sperm in massive synchronized events that depend on moonlight intensity. Nocturnal predators time their hunts to moon phases, when prey is more or less visible. The dung beetle, that humble navigator of the night, uses the polarized light of the moon to roll its precious cargo in straight lines. Without moonlight, studies show these beetles become hopelessly disoriented, rolling in circles, wasting precious energy. It's a small example, but it illustrates a larger truth. The moon's light is woven into the behavioral fabric of life on Earth in ways we're only beginning to understand. Now we arrive at what many scientists consider the most catastrophic consequence of losing the moon. Not the tides, not the darkness, something far more fundamental: the stability of Earth's axial tilt. Here's something most people don't fully appreciate. Earth doesn't spin perfectly upright. Our planet is tilted on its axis at approximately 23.4 degrees, relative to our orbital plane around the Sun. This tilt is responsible for something rather important: seasons. When the northern hemisphere tilts toward the Sun, it experiences summer, while the southern hemisphere experiences winter, and vice versa. This axial tilt varies naturally over time, but only within a narrow range of about 22.1 to 24.5 degrees, cycling over roughly 41,000 years. These small variations contribute to long-term climate cycles, including ice ages, but they're gradual enough that life can adapt. The key word here is gradual. The reason Earth's tilt remains relatively stable is our massive moon. Like a gyroscopic stabilizer, the moon's gravitational influence dampens the natural wobbles that would otherwise cause our axis to shift dramatically. Without it, Earth would be subject to gravitational tugging from Jupiter and Venus, which would cause our axial tilt to fluctuate wildly, potentially anywhere from 0 degrees to nearly 90 degrees over millions of years. This isn't speculation. We have a real-world example: Mars. The red planet has no large moon to stabilize it. Phobos and Deimos are tiny, captured asteroids, and scientists have calculated that its axial tilt has varied chaotically between 10 and 60 degrees over its history. Some models suggest Mars may have even temporarily tilted beyond 80 degrees. Imagine what that would mean for Earth. At 0 degrees of tilt, there would be no seasons. The equator would be perpetually hot, the poles perpetually frozen, and the climate zones that support agriculture and diverse ecosystems would cease to exist. At extreme tilts, approaching 90 degrees, different parts of Earth would experience months of continuous daylight, followed by months of complete darkness. The temperature extremes would be beyond anything life has adapted to handle. Now, these extreme axial shifts wouldn't happen overnight. Even without the moon's stabilizing influence, the wobbles would develop over thousands to millions of years. But here's the disturbing part: smaller, more rapid fluctuations would begin almost immediately. Computer models suggest that without the moon, Earth's axis could shift by several degrees within just a few million years, a blink of an eye in geological terms. For a civilization that has developed agriculture, cities, and infrastructure based on predictable climate patterns, even small shifts would be devastating. Here's another moon fact that might surprise you. Our days used to be much shorter. Billions of years ago, when the moon was newly formed and orbiting much closer to Earth, our planet spun so fast that a day lasted only about 6 hours. Over billions of years, the moon has been gradually slowing Earth's rotation through tidal friction. The mechanism works like this. As the moon's gravity creates tidal bulges in Earth's oceans, the friction of all that moving water acts as a brake on our planet's spin. It's an incredibly slow process, adding roughly 1.4 milliseconds to the length of a day every century. But over geological time scales, it adds up. When dinosaurs roamed the Earth about 70 million years ago, a day was roughly 23.5 hours long. The moon itself is slowly drifting away from Earth as a consequence of this same energy transfer, receding at approximately 3.8 centimeters per year. Astronauts from the Apollo missions placed reflectors on the lunar surface that allows scientists to measure this distance with extraordinary precision using laser-ranging experiments. If the moon vanished, this braking effect would largely disappear. The sun still exerts some tidal friction, but it's much weaker. Over long time scales, Earth would actually begin to spin faster again. But in the short term, something more chaotic would happen. The sudden removal of the moon's gravitational influence would cause Earth's rotation to change slightly but noticeably. The planet's shape itself. Remember that slight bulge toward the moon we discussed would need to readjust. Mass would redistribute. The moment of inertia would change. These adjustments would cause variations in the length of day and potentially trigger seismic activity as Earth's crust shifted to accommodate its new shape. We already observe similar phenomena on a much smaller scale. Major earthquakes can redistribute enough mass to measurably change Earth's rotation. The 2011 earthquake in Japan, for instance, shortened the day by approximately 1.8 microseconds. Now imagine the kind of redistribution that would occur if an object containing 7.35 times 10 kilograms of gravitational influence suddenly ceased to exist. We've touched on some of the ecological impacts already. But let's dive deeper into how comprehensively the moon's disappearance would devastate Earth's biosphere. Because the truth is, life on this planet is lunar life. We just don't think about it that way. Start with the marine ecosystems. The intertidal zone, that strip of coastline between high and low tide marks, is one of the most productive ecosystems on Earth. It supports an extraordinary diversity of life: anemones, barnacles, mussels, crabs, sea stars, countless fish species that feed and breed there, and the seabirds that depend on all of them. This entire ecosystem exists because of tides. Reduce tidal amplitude by 2/3, and you don't just shrink this habitat. You fundamentally transform it. Estuaries, where rivers meet the sea, would be particularly hard hit. These brackish zones depend on tidal mixing to maintain their unique chemistry, which supports species found nowhere else. Salmon, for instance, rely on tidal patterns to navigate during their spawning runs. Alter those patterns, and you disrupt reproduction cycles that have been fine-tuned over millions of years of evolution. Then there's the phenomenon of mass spawning events. On coral reefs around the world, hundreds of species synchronize their reproduction to lunar cycles, releasing eggs and sperm simultaneously in spectacular underwater snowstorms. The full moon, after the first big water temperature rise of spring, triggers mass spawning on Australia's Great Barrier Reef, an event so precisely timed that scientists can predict it to within a day or two. Without the moon, these synchronization cues disappear. Reproduction rates would plummet. Coral populations, already under severe stress, would face another existential threat. On land, the disruptions would be equally profound. Many animals use moonlight to regulate their activity patterns. Lions hunt more successfully on dark nights when their prey can't see them coming. Conversely, many prey species restrict their activity to brighter nights when they can better detect predators. These behavioral adaptations represent evolutionary responses to millions of years of predictable lunar cycles. Remove the moon, and predator-prey dynamics shift in unpredictable ways. Insects, which many people don't associate with the moon, are perhaps the most dramatically affected group. Moths navigate by maintaining a fixed angle to the moon, a behavior that artificial lights tragically exploit. Many insect species time their emergence, mating flights, and migration to lunar phases. Mayflies, which emerge in enormous swarms during specific lunar conditions, are a crucial food source for freshwater fish. Disrupt that emergence, and you disrupt entire freshwater food webs. Even plants respond to the moon, though this is less well understood than animal behaviors. Some research suggests that plants may time certain processes, like sap flow, to lunar cycles. Farmers in many traditional cultures have long planted according to moon phases. And while modern science is still evaluating these practices, there's intriguing evidence that lunar gravitational effects may influence plant biology in subtle ways. So far, we've focused largely on natural systems. But let's bring this closer to home. What would losing the moon mean for human society? How would our species, so remarkably adaptable, cope with such a fundamental change to our environment? The immediate effects would be chaotic, but potentially manageable for wealthy, technologically advanced nations. Coastal flooding would cause billions of dollars in damage, but rich countries have dealt with floods before. The darkness would be disorienting, but addressable with artificial lighting. The true challenges would emerge more gradually, and they would test the limits of human ingenuity. Consider agriculture. Modern industrial farming already struggles with climate unpredictability. Add the eventual destabilization of seasons caused by axial wobble, and the carefully calibrated systems that feed 8 billion people would begin to fail. Crop varieties bred for specific temperature ranges and day lengths would find themselves mismatched to their environments. Planting calendars developed over centuries would become useless guides. The fishing industry would face immediate and severe impacts. Commercial fishing depends on understanding fish behavior, which is deeply tied to tidal patterns and lunar cycles. Trawlers know when and where to find fish, because those fish follow predictable routines. Disrupt the tides, and you disrupt these patterns. Fishing communities that have sustained themselves for generations would find their traditional knowledge suddenly obsolete. Navigation, too, would be affected in subtle but significant ways. While modern ships use GPS and sophisticated instruments, Traditional celestial navigation used the moon as a key reference point. More importantly, tidal predictions that shipping depends on to navigate harbors and coastal waters would need to be entirely recalculated. Ports designed around certain tidal ranges might become unusable. But perhaps the most profound impact on human civilization would be psychological and cultural. The moon has been central to human consciousness since before we were fully human. Our earliest art depicts it. Our oldest calendars track it. Every culture on Earth has moon myths, moon gods, moon festivals. The Chinese Mid-Autumn Festival, the Jewish Passover, the Islamic Ramadan, Hindu Karwa Chowth. All these observances are tied to lunar cycle. What happens to the human psyche when such a fundamental symbol simply vanishes? How do we cope with losing something so ancient, so present, so woven into our very sense of what the sky should look like? The grief would be profound, not because we need the moon to survive in our modern, technologically buffered world, but because we need it to feel at home in the universe. The night sky without the moon would feel broken, amputated, wrong in a way that would take generations to accept. Before we continue with the cascade of disasters, let's pause to appreciate the scientific reasoning behind these predictions. How do we know what would happen if the moon disappeared? After all, we can't run the experiment. We can't remove the moon and see what happens. So how confident can we really be about these scenarios? The answer lies in our understanding of physics, our observations of other planets, and increasingly sophisticated computer models that can simulate planetary dynamics over millions or billions of years. We understand tides with extraordinary precision. The equations governing gravitational attraction were worked out by Isaac Newton over 3 centuries ago and refined by Einstein's general relativity. We can predict tides anywhere on Earth at any time, with accuracy measured in centimeters. This same mathematical framework tells us exactly what would happen to Earth's oceans if the moon's gravitational influence vanished. For axial stability, we look to Mars. The red planet serves as a natural laboratory for understanding what happens to a world without a large, stabilizing moon. Mars's axial tilt has wandered chaotically throughout its history, and we have geological evidence of the climate chaos this caused. Ancient river channels suggesting past warmth ice caps that have grown and shrunk dramatically. Layered deposits that record wildly varying climate conditions. Computer simulations have become powerful enough to model Earth's dynamics over hundreds of millions of simulated years. Varying parameters like the presence or absence of the moon. These models consistently show that without lunar stabilization, Earth's axial tilt would become chaotic on timescales of millions to tens of millions of years. Different modeling teams using different approaches have converged on similar conclusions, giving scientists confidence in these predictions. The biological predictions are based on decades of observational research documenting how organisms respond to lunar cycles. Scientists have tracked coral spawning, insect emergence, predator hunting success, and countless other phenomena, building a detailed picture of how deeply the moon is embedded in Earth's ecological rhythms. While we can't predict every consequence of the moon's disappearance, we can confidently predict that the disruption would be massive. Let's pause here for a moment and take stock of what we've covered. In the hours, days, and years following the moon's disappearance, we would witness immediate tidal chaos as Earth's oceans redistribute, causing flooding in some areas and sudden drops in others. The reduction of tides to roughly 1/3 of their current strength, devastating intertidal ecosystems worldwide. The plunging of nighttime into unprecedented darkness, affecting countless species that depend on moonlight. The beginning of long-term axial instability that would, over millions of years, make Earth's climate unrecognizable. And we're only halfway through our exploration. In Part 2, we'll venture into even more unsettling territory. We'll examine how the moon's disappearance would affect Earth's magnetic field and our protection from solar radiation. We'll explore the volcanic and seismic consequences of removing such a massive gravitational influence. We'll consider how different cultures and religions would respond to such an existential event. And we'll ask the ultimate question. Could life on Earth survive long enough to adapt to this new, moonless reality? The moon has been with us since before life crawled from the sea. It has watched over every human civilization that ever rose and fell. It has inspired art, science, religion, and romance. And while it's not going anywhere anytime soon, understanding what we would lose without it helps us appreciate just how fortunate we are to have it. So go outside tonight if you can. Look up at that pale circle in the sky. Think about the ancient collision that created it, the billions of years it has spent slowly retreating from us, the countless organisms whose lives are timed to its cycles, and the stability it provides to the planet you call home. That's not just a rock up there. That's our partner in the cosmic dance. That's the guardian that makes our existence possible. That's home, reflected back at us from 384,400 kilometers away, and we should never, ever take it for granted. Here's something that might surprise you. The moon doesn't just pull on Earth's oceans. It pulls on everything. The solid rock beneath your feet rises and falls by about 30 centimeters twice daily, responding to the same gravitational forces that create ocean tides. We call these earth tides, or body tides, and while you can't feel them because everything around you moves together, they're very real and very measurable. Scientists at CERN, home of the Large Hadron Collider, actually have to account for earth tides in their particle physics experiments. The 27-kilometer circumference of the collider ring expands and contracts by about a millimeter as the moon passes overhead, enough to affect the precision measurements they're trying to make. That's how significant lunar gravitational influence is, even on solid matter. Now, imagine what happens when that constant kneading of Earth's interior suddenly stops. For billions of years, the moon has been flexing our planet's crust and mantle, generating friction and heat deep underground. This tidal heating contributes to Earth's internal heat budget, though scientists debate exactly how much. Some estimates suggest lunar tidal forces add several terawatts of heat to Earth's interior, a small but non-negligible contribution to the geological activity that keeps our planet dynamic. Remove the moon, and you don't just remove that heat source. You also remove a rhythmic stress pattern, that the planet's interior has adjusted to over billions of years. Magma chambers that have found equilibrium under certain stress conditions would suddenly experience different forces. Fault lines that slip in patterns influenced by tidal stress would behave differently. There's growing scientific evidence that earthquakes and volcanic eruptions are influenced by tidal forces. A 2016 study published in Nature Geoscience found that the largest earthquakes tend to occur during periods of high tidal stress. Research on volcanoes has shown correlations between eruption timing and lunar cycles, particularly for volcanoes with shallow magma chambers that are more sensitive to small pressure changes. If the moon vanished, the immediate effect would be the cessation of these regular stress cycles. But immediate, in geological terms, doesn't mean instantaneous chaos. The Earth's interior operates on long time scales. What we might see over years to decades is a subtle shift in patterns of seismic and volcanic activity as the planet's crust and mantle adjusted to the new stress regime. Some volcanologists speculate that the change could trigger increased activity in certain regions, as magma that was held in check by regular tidal compression found new pathways to the surface. Others suggest that without tidal pumping, some volcanic systems might actually become less active over time. The honest answer is that we don't know for certain, because we've never observed a planetary system suddenly lose its major moon. What we can say with confidence is that Earth's geological behavior would change. The planet we know, with its particular patterns of earthquakes and eruptions, would slowly become a different geological entity. For a species that has built nuclear power plants on fault lines and cities in the shadows of volcanoes, any change in these patterns, even gradual ones, could be catastrophic. Deep beneath your feet, some 2,900 kilometers down, lies Earth's outer core, a churning ocean of liquid iron and nickel heated to temperatures exceeding 4,000 degrees Celsius. This molten metal is in constant motion, driven by heat escaping from the even hotter inner core and by Earth's rotation. These movements generate electric currents, which in turn create the magnetic field that surrounds our planet like an invisible cocoon. This magnetic field, the magnetosphere, is far more important than most people realize. It extends tens of thousands of kilometers into space, deflecting the constant stream of charged particles flowing from the sun, known as the solar wind. Without this shield, those particles would strip away our atmosphere and bombard the surface with radiation. Mars, which lost its global magnetic field billions of years ago, serves as a cautionary tale. Its atmosphere was largely blown away by the solar wind, transforming it from a potentially habitable world into the cold, desiccated desert we see today. So what does the moon have to do with Earth's magnetic field? More than you might think. Some researchers have proposed that lunar tidal forces contribute to the stirring of Earth's outer core, helping to maintain the dynamo effect that generates the magnetic field. A 2016 study by scientists at CNRS in France suggested that the moon's gravitational influence could account for a significant portion of the energy driving core convection. This remains a topic of active scientific debate. Earth's core dynamo is incredibly complex. driven by multiple heat sources and fluid dynamics that we're still working to fully understand. If lunar tidal forces do contribute meaningfully to core stirring, then removing the moon could, over geological timescales, weaken our magnetic field. A weaker magnetic field would have profound consequences. Solar storms, which currently cause only minor disruptions, like beautiful auroras and occasional satellite problems, would become far more dangerous. Major solar events could damage power grids, disable satellites, and expose anyone outdoors, particularly at high altitudes or latitudes, to harmful radiation doses. Over longer timescales, a weakening magnetosphere could allow the solar wind to slowly erode Earth's atmosphere, particularly the lighter elements like hydrogen. This wouldn't happen overnight, or even over centuries. We're talking millions of years. But the trajectory would be toward a less hospitable planet, one that slowly lost the atmospheric protection that makes surface life possible. It's worth noting that Earth's magnetic field has weakened and reversed many times throughout history without lunar influence changing. The field is inherently variable, but any additional stress on the dynamo system, including the loss of tidal energy input, could accelerate or exacerbate existing weaknesses. In a moonless future, our invisible shield might become increasingly unreliable. We've spent considerable time on the physical and biological consequences of losing the moon. But humans are not purely physical beings. We are creatures of meaning, of story, of symbol. And the moon has been central to human meaning-making since before recorded history. Its disappearance wouldn't just change our planet, it would change our souls. Consider the sheer ubiquity of lunar symbolism across human cultures. The crescent moon appears on the flags of more than a dozen nations. The moon goddess appears in virtually every ancient pantheon: Selene and Artemis in Greece, Luna and Diana in Rome, Change in China, Tsukuyomi in Japan, Mani in Norse mythology, Ix, Chel among the Maya, Khonsu in Egypt. These weren't minor deities. They were central figures in religious practice, invoked in fertility rites, harvest festivals, and ceremonies marking life's transitions. The Islamic calendar is entirely lunar, with months beginning at each new moon sighting. Ramadan, the holiest month in Islam, shifts through the solar year because it follows lunar rather than solar cycles. The Jewish calendar is lunar-solar, with months tied to the moon and periodic adjustments to keep holidays aligned with seasons. Easter, the most important Christian holiday, is calculated based on the first full moon after the spring equinox, a formula established at the Council of Nicaea in 325 CE. What happens to these traditions when there is no moon to observe? The Islamic call to begin Ramadan based on moon sighting would become impossible. The Jewish blessing over the new moon, recited monthly for millennia, would lose its object. The Easter calculation would become meaningless. These aren't trivial matters for the billions of people whose lives are structured around these observances. Beyond organized religion, the moon permeates human culture at every level. Our languages bear witness to its importance. Lunatic and moonstruck preserve ancient beliefs about lunar influence on the mind. poets from every era have written about the moon's beauty, mystery, and emotional resonance. Lovers have promised to love each other to the moon and back. Musicians have serenaded it. Artists have painted it. Architects have designed buildings to frame it. The moon has served as humanity's first stepping stone into the cosmos. 12 human beings have walked on its surface, an achievement that inspired generations and demonstrated what our species could accomplish when we reached beyond ourselves. The Apollo program remains one of humanity's greatest technological and cultural achievements. Without the moon, we would lose not just a celestial body, but a destination, a symbol of aspiration, a proof of what's possible. The psychological impact of the moon's disappearance might be the hardest to quantify, but among the most significant. Humans have looked up at the moon every night for hundreds of thousands of years. It has been our companion through every stage of civilization, from the first campfires to the present day. To lose it would be to lose something fundamental to human experience, something that connects us to every generation that came before. Imagine trying to explain the moon to children born after its disappearance. Yes, there used to be a glowing sphere in the night sky. It changed shape over the course of a month. It pulled the oceans toward it. People walked on it once. How would that sound? Like a fairy tale, like mythology, like something too wondrous to have been real. The moon's absence wouldn't just impoverish science and ecology. It would impoverish the human spirit, leaving us stranded under a sky that felt emptier, a universe that felt colder, a night that no longer offered the comfort of that familiar, watchful presence. We discussed the immediate tidal chaos in Part 1. But the long-term effects on ocean circulation deserve deeper exploration. Because the moon doesn't just create tides. It helps drive the massive conveyor belt of ocean currents that distributes heat around the planet and regulates global climate. The thermaline circulation, sometimes called the global ocean conveyor belt, is a system of deep water currents that moves heat from the tropics toward the poles. Warm surface water flows north in the Atlantic, releases its heat to the atmosphere, which is why Western Europe is much warmer than its latitude would suggest, becomes denser as it cools and becomes saltier, then sinks to the deep ocean and flows back south. This process takes roughly 1,000 years to complete a full cycle. Tidal mixing plays a crucial role in this system. As tides slosh water over underwater ridges and continental shelves, they create turbulence that mixes different layers of the ocean. This mixing helps bring deep, nutrient-rich water toward the surface, fueling marine productivity, and it helps drive the density differences that power the thermaline circulation. Scientists have estimated that tidal mixing accounts for roughly half the energy that drives ocean circulation, with the other half coming from wind. A 2000 study in Nature found that without tidal mixing, the deep ocean would become stagnant, stratified into layers that barely interact with each other, reduce tides by 2/3, as would happen with only solar tidal forces remaining, and you significantly weaken this mixing. The consequences would unfold over decades to centuries. The thermaline circulation would slow, heat distribution around the planet would change. Some regions would become warmer, others would become dramatically colder. The North Atlantic, in particular, would be affected. The Gulf Stream, which carries warm water northward and keeps Europe temperate, depends on deep water formation in the Norwegian and Labrador seas. If reduced tidal mixing weakened this deep water formation, the Gulf Stream could slow or shift. London, which sits at the same latitude as Calgary, could experience Canadian winters. Ireland could see regular snow. The agricultural systems that feed hundreds of millions of Europeans would need to adapt or fail. Meanwhile, the deep ocean would become increasingly oxygen-depleted as circulation slowed. Today, the conveyor belt carries oxygenated surface water to the deep sea, allowing life to exist even in the abyssal depths. Without adequate mixing, these depths could become anoxic dead zones, hostile to complex life. The deep-sea ecosystems that scientists are only beginning to explore, hydrothermal vent communities, cold seep habitats, abyssal plains teeming with strange creatures, could slowly suffocate. The changes wouldn't happen overnight. Ocean circulation operates on long time scales, and the system has considerable inertia. But within a few centuries of the moon's disappearance, the oceans would be fundamentally different, less mixed, less productive, less able to moderate climate extremes. The blue marble we know would become something else entirely. Let's zoom out now, way out. We've been discussing consequences on timescales of days to centuries. But the moon has been with Earth for 4.5 billion years, and life has been evolving on this planet for nearly 4 billion of those years. To truly understand what we would lose, we need to think in deep time. When the moon first formed, it was perhaps 10 times closer to Earth than it is today. The early moon would have appeared enormous in the sky, and its gravitational effects would have been correspondingly more powerful. Days were only about 6 hours long. Tides were measured in kilometers, not meters, with walls of water sweeping across the young planet's surface. Some scientists have proposed that these extreme early tides may have played a crucial role in the origin of life. The tidal zones of early Earth, regularly flooded and exposed, heated and cooled, concentrated and diluted, would have created ideal conditions for complex chemistry. Molecules could have been brought together, energized, and then preserved as the tides retreated. The rhythmic nature of tides might have provided the repetitive conditions necessary for self-replicating molecules to emerge and multiply. This is speculative, of course. We don't know exactly how life began on Earth, and we may never know with certainty. But the moon's role in creating dynamic, energetic coastal environments cannot be dismissed. If life did arise in tidal zones, as many researchers suspect, then we owe our very existence to lunar gravitational influence. As life evolved, it adapted to lunar rhythms at every level. We've discussed some of these adaptations: coral spawning, sea turtle navigation, predator-prey dynamics. But the entrainment goes deeper than behavior. Many organisms have internal circadian clocks, biological rhythms that cycle with the 29.5-day lunar month independent of any external cues. Marine worms of the species Platinares dumerilli spawn in mass events tied to the moon's phase, and laboratory studies have shown that they maintain this rhythm even when isolated from any lunar light or tidal cues. The rhythm is internally generated, encoded in their genes, the product of hundreds of millions of years of evolution under lunar influence. Humans, too, may carry vestiges of lunar rhythms. The human menstrual cycle averages about 29.5 days, remarkably close to the lunar month. While modern research has found little evidence of synchronization between menstrual and lunar cycles, some scientists have suggested that the comparative similarity is not coincidental, that it may reflect ancient evolutionary adaptation to lunar timing that has become decoupled from the moon itself over millennia of indoor living. The moon has also influenced the long-term evolution of Earth's rotation and climate stability, as we discussed earlier. But consider what this means from a deep time perspective. Every complex organism on Earth, every vertebrate, every plant, every fungus, evolved on a planet stabilized by its moon. We are all, in a sense, children of that stability. Our forms, our behaviors, our very DNA reflect billions of years of evolution on a world with predictable seasons and moderate climate fluctuations. Remove the moon, and you don't just change current conditions. You sever a connection to deep evolutionary history. The organisms of a moonless future Earth would face selective pressures completely unlike those that shaped their ancestors. Some lineages would adapt, many would not. The biosphere that emerged over millions of years would bear little resemblance to the one we know. Let's return to the purely aesthetic for a moment, because losing the moon wouldn't just change our planet's functioning. It would fundamentally alter the experience of looking up at night. On one hand, stargazers might initially celebrate the moon, while beloved is also the bane of amateur astronomers. Its bright light washes out fainter celestial objects, making it difficult to observe galaxies, nebulae, and all but the brightest stars when the moon is up. Professional observatories plan their observations around lunar phases, scheduling time-sensitive work on faint objects during the darkest nights around new moon. Without the moon, every night would be a dark night. The Milky Way would blaze across the sky in its full glory, visible even from locations with modest light pollution. Faint meteor showers that currently go largely unnoticed would become spectacles. The zodiacal light, that faint pyramid of luminescence caused by sunlight scattering off dust in the plane of the solar system, would be visible whenever conditions were clear. But this astronomical bounty would come at a terrible cost. The sky would feel empty, unbalanced. For thousands of years, humans have navigated, literally and metaphorically, by the moon. Ancient sailors used it to estimate time at night. Travelers used it to light their way. Its monthly cycle provided a natural calendar that structured human activities long before written records. The phases of the moon have given us some of our most universal metaphors: waxing and waning, cycles of growth and decline, the monthly renewal of the new moon, and the fullness of potential in the complete orb. Werewolf legends, lunacy, moonshine, honeymoons, all these concepts derive meaning from the moon's presence. Without it, they would become incomprehensible to future generations. Solar eclipses would become impossible. Those rare, awe-inspiring events when the moon passes directly between Earth and Sun, revealing the solar corona in a ring of ethereal light, would be relegated to historical records and computer simulations. Future humans would watch footage of past eclipses with the same wonder and disbelief with which we might watch videos of now extinct animals. They would know, intellectually, that such things once happened, but they would never experience them. And lunar eclipses, those blood-red moons that have terrified and inspired humanity throughout history, would obviously be impossible as well. No more would crowds gather to watch Earth's shadow slowly swallow our companions. No more would that rusty orange glow send shivers down spines or prompt prayers from the faithful. The night sky, without the moon, would be like a face missing an eye. More stars would be visible, yes, but something essential would be absent. Something that made the night feel complete, that gave the darkness a companion, that reminded us, every time we looked up, that we are not alone in the cosmos. We've painted a fairly apocalyptic picture. Tidal chaos, ecosystem collapse, climate destabilization, weakening magnetic fields, cultural trauma. But let us address the question you've probably been asking since the beginning. Could human civilization actually survive the moon's disappearance? The honest answer is probably, at least in the short term. Humans are remarkably adaptable. We've survived ice ages, supervolcanic eruptions, plagues, and wars. We've spread to every continent and adapted to environments from the Arctic to the Sahara. We've developed technologies that buffer us from environmental extremes in ways our ancestors couldn't have imagined. The immediate tidal disruptions would cause enormous damage and loss of life, but they wouldn't be extinction-level events for humans. We would rebuild coastal cities further inland. We would develop new fishing practices adapted to reduced tides. We would light our nights artificially, as we already do in most urban areas. The longer-term challenges would be more severe but more gradual. Axial instability would develop over thousands to millions of years, giving civilization time to adapt or develop mitigation strategies, assuming civilization endures that long. Changes in ocean circulation would unfold over centuries, allowing for gradual adjustment of agricultural systems and population distributions. But survive is a low bar. The question is whether we could maintain anything resembling our current civilization. With its 8 billion people, its complex global supply chains, its scientific and cultural achievements. And here the answer becomes much less certain. Our food systems are extraordinarily dependent on stable climate. Even the relatively modest climate changes we are currently experiencing due to greenhouse gas emissions are causing significant disruptions to agriculture. The kind of seasonal chaos that would eventually result from axial instability would make our current climate challenges look trivial. Crop failures would become common. Famines would likely reduce human population to a fraction of current levels. The collapse of marine ecosystems would eliminate a major source of protein for billions of people. Coastal communities that have sustained themselves through fishing for millennia would need to find entirely new ways of living. The economic and social disruptions would be immense. And then there's the psychological and cultural dimension. Humans have never faced an existential challenge quite like this. Not a disaster caused by nature or by our own actions, but the simple absence of something that has always been there. How would societies respond to such a loss? With resilience and adaptation, with despair and collapse, with religious fervor or nihilistic abandon? We truly don't know, because we've never been tested in this particular way. Perhaps the fairest assessment is this: some humans would survive, and some form of human civilization would likely persist. But the world that emerged would be profoundly different from the one we know, not just physically and ecologically, but culturally and spiritually. We would be a species diminished, having lost not just a celestial body but a piece of what made us who we are. Beyond human survival, what about life in general? Evolution is a powerful force. Given enough time, life has adapted to every environment Earth has offered, from boiling hot springs to frozen Antarctic lakes, from the crushing pressures of the deep ocean to the thin air of mountain peaks. Could life adapt to a moonless Earth? Over very long timescales, the answer is almost certainly yes. Life is tenacious. It finds a way. Species that currently depend on lunar cues would either evolve alternative timing mechanisms or go extinct, replaced by others that don't require lunar signals. Ecosystems would restructure around new tidal patterns and new selection pressures. We have precedent for this kind of adaptation. When the asteroid struck 66 million years ago and wiped out the dinosaurs, it wasn't the end of life on Earth. It was a transition. The survivors adapted to the new conditions, diversified, and eventually filled the ecological niches left vacant. The mammals that had been small, marginal creatures became the dominant large animals. Evolution doesn't stop, it pivots. But adaptation takes time, and the transition period would be brutal. The mass extinction event at the end of the Cretaceous killed an estimated 75% of all species. A similar or larger extinction might follow the Moon's disappearance, as ecosystems collapsed faster than evolution could respond. The axial instability would pose the greatest long-term challenge. Life on Earth has never had to cope with the kind of rapid, chaotic climate shifts that would result from an unstabilized axis. The Martian example suggests that such worlds can become essentially uninhabitable for complex surface life, at least as we understand it. But Earth has advantages Mars lacks, even without the Moon. Our planet is larger, with a thicker atmosphere and stronger gravity to hold onto that atmosphere. We have liquid water and active geology that recycles elements essential for life. Even under severe climate stress, life would likely persist in refugia, pockets of relative stability where conditions remained tolerable. Microbial life, in particular, would almost certainly survive. Bacteria and archaea are incredibly hardy, capable of surviving extreme temperatures, radiation, and chemical conditions. Even if complex surface life collapsed, the microbial biosphere would persist in deep aquifers, hot springs, and ocean sediments. The question is whether complex life could recover and rediversify over the hundreds of millions of years following the Moon's loss. If axial instability remains severe, repeatedly pushing the climate from one extreme to another, complex ecosystems might never gain a foothold. Earth could become a microbial planet once again, resembling the world that existed for the first 2 billion years of life's history, before complexity emerged. Alternatively, some complex lineages might evolve to cope with unstable conditions, developing flexible life cycles, extreme tolerance for environmental variation, or underground or deep-sea habits that buffer them from surface chaos. Life finds a way, as the saying goes. But it wouldn't be our way. It would be something new, something strange, something adapted to a world we would barely recognize. Before we conclude, let's address the elephant in the room. Could the moon actually disappear? Is there any realistic scenario in which we might face this crisis? The short answer is no. The moon is not going anywhere. It's locked in a stable gravitational dance with Earth, and there is no known natural process that could remove it on any time scale we need to worry about. Yes, the moon is slowly drifting away from Earth, but at 3.8 centimeters per year. It would take billions of years for it to reach a distance where its effects became negligible, and by that time the sun will have entered its red giant phase and likely engulfed the inner planets anyway. Long before the moon drifts too far, our solar system will face much bigger problems. What about an asteroid impact? The moon has been heavily bombarded throughout its history, as its cratered surface attests. But an impact large enough to destroy the moon or knock it out of orbit would require an object of immense size, probably comparable to the moon itself. Such an impact hasn't happened in billions of years, and there's no known object on a trajectory that would threaten the moon in this way. Could aliens remove it? Could some advanced civilization decide to harvest the moon for raw materials? We're now deep in science fiction territory. While we can't rule out the existence of advanced extraterrestrial civilizations, we have no evidence that any such civilization has visited our solar system or has designs on our natural satellite. The moon's disappearance is, in practical terms, impossible. This entire exploration has been an exercise in imagination, a thought experiment designed to illuminate how much we depend on something we usually take for granted. And perhaps that's the real value of considering impossible scenarios. By imagining what we would lose, we gain appreciation for what we have. By contemplating catastrophe, we cultivate gratitude. The moon will rise tonight, as it has every night since before human eyes evolved to see it. Understanding what its absence would mean helps us see its presence with new wonder. So here we are, at the end of our journey through a moonless world. We've watched oceans convulse, ecosystems collapse, climates destabilize, and human spirits falter. We've contemplated the deep time connection between our moon and the origin of life itself. We imagined night skies stripped of their most familiar landmark and future generations, who would know the moon only from stories. And through it all, I hope one thing has become clear. The moon is not optional. It's not decoration. It's not just a romantic backdrop or a convenient nightlight. The moon is fundamental to what Earth is and to what life on Earth has become. We are lunar creatures on a lunar planet, shaped by tides and cycles and stability that flow from that pale sphere in the sky. The Apollo astronauts who walked on the moon described a strange experience when they looked back at Earth from the lunar surface. They saw their home world as a small, fragile, beautiful oasis in the vastness of space. They came back transformed, many of them becoming environmentalists and advocates for planetary stewardship. They had seen something that changed their perspective forever. We don't need to travel to the moon to have a similar shift in perspective. We just need to understand what the moon means to us. And now you do. You know about the tides it drives, the axis it stabilizes, the ecosystems it regulates, the cultures it has shaped, the very possibility of your existence it has enabled. The moon is a gift. It's a gift from the violence of the early solar system, from that ancient collision between Earth and Theia that could have destroyed our young planet, but instead gave it a companion. It's a gift that has kept on giving for 4.5 billion years, and will continue to give 4 billions more. So tonight, if it's clear where you are, go outside, look up, find that familiar glow in the sky. Think about the tides it's pulling right now, the creatures timing their lives to its light, the stability it's providing to your world. Think about the generations of humans who have looked at that same light, from cave painters to astronauts, and felt something they couldn't quite name, and then say thank you. Not out loud, necessarily, just in your heart. Thank you for the tides. Thank you for the seasons. Thank you for the stable climate and the rhythm of life. Thank you for being there, night after night, century after century, eon after eon. Thank you for making Earth the kind of place where creatures like us could emerge and wonder and look up and ask questions about the universe. The moon doesn't need our gratitude, of course. It's just a ball of rock and dust, orbiting in silence. But we need to feel that gratitude. We need to recognize, in our bones, how connected we are to the cosmic dance we're part of. Because that's the lesson of this thought experiment. Not that we should fear the moon's disappearance, which will never happen, but that we should love the moon's presence, which is happening right now, and will happen again tomorrow night, and the night after that, for as long as there are eyes on Earth to witness it. We are children of the moon. Let's never forget it. Thank you for joining me on this journey tonight. If you made it all the way to the end, drop a comment and let me know what part of this exploration surprised you the most. Was it the tidal biology, the axial stability, the cultural depth of our lunar connection? I'd love to hear your thoughts. And if you're watching this in the middle of the night somewhere, maybe take a moment to step outside before you go to sleep. The moon might be up, and if it is, you'll see it differently now. I promise you that. Until next time, stay curious, stay grateful, and keep looking up.